Okay, now we're talking about the harmonic oscillator, and up to now we've done um, uh, the particle in a box as a quantum mechanical system representing an electron bound um, by the constraints of the potential box. But for molecular vibration, we have a different type of potential energy that restricts or dictates how the electronic domain can oscillate. Okay, so we're going to use a harmonic oscillator as our quantum mechanical system. But before we do that, I want to show you the classical result so you have something to compare. So if you start with a diatomic molecule, well, actually it's not a molecule, just a diatomic thing. So two masses on a spring. So M1 on a spring, M2. Okay, so here is the position of mass 1, and this distance right here is the equilibrium distance. Okay, so if you were to take mass 1 and the mass 2 and stretch it, what's going to happen is there's going to be a restoring force X back this direction because you've stretched the spring now beyond the equilibrium position. Likewise, if you smash the spring down, so you compress the spring down, there's going to be a restoring force that direction. Okay, so stretch it, the restoring force is going to go opposite way. Compress it, the restoring force is going to go the opposite way. So that restoring force is the spring pushing back against you if you've pushed it smaller than the equilibrium distance. Okay, and this stretching here, this would be known as the displacement x, and that's equal to r minus r equilibrium. So this is its r value. So you subtract off the equilibrium value, and that'll give you this x distance. Likewise here. Okay, so the restoring force this is known as Hooke's law. So the restoring force F of x is equal to minus kx times, kx times x. X is everywhere. Well, this little x represents that we're only looking at the x direction. Okay, so one dimension. Negative sign because it's a restoring force, and so if you're pulling it this way, so if I'm pulling it this way, I'm putting a force this direction, but then the restoring force is going back the other way, so it's going opposite the direction that it's being pulled. Likewise, if I'm pushing this direction, the restoring force is opposite of the direction of the displacement. Whoops. There we go. Okay. I got tied up in the, really tied up. There we go. Sorry about that. Didn't realize. Okay. So, so this is Kx. This is known as our spring constant. And this is related to the strength of the spring. So bigger strength or stiffness of the spring, the bigger the spring constant. Cool? Okay. Now, quantum mechanically, or I shouldn't say quantum mechanically, but the classical treatment is looking at the energy of the oscillation. Sorry, my handwriting's sucking today. So energy equals energy kinetic plus energy potential. Okay. So the potential energy, kinetic energy we'll get to in a second, but the potential energy is determined by finding the so the negative derivative of the potential is the force constant, or sorry, is the force, restoring force. Okay, so minus d dx of the potential energy is equal to the force. Cool? Which means if we want to take or determine what the potential energy is of this, what we need to do is take the integral or the negative integral. So if we take the negative integral of negative kx dx, what we get then is the potential. So that is negative, negative. That makes it a positive. So the integral of kx dx, well, that's just 1/2 kx squared. Cool. So this is our potential energy. So 1/2 kx squared. Okay, so this is where Hooke's law comes from. And then now we want to know what our kinetic energy is. So the kinetic energy, we've got, so I'm going to kind of do a little aside. Actually, I'm going to pause, just erase. Okay, so the kinetic energy, I'm going to say, well, 1/2 mv squared or mv squared over 2. Okay, so I'm going to quickly do a little rearrangement of 1/2 mv squared, and I'm going to multiply this by m over m, which is going to give me m squared v squared over 2m. Follow me? All right, if I do that, what I can then say is this is the same thing as p squared over 2m. And you'll see why I'm doing this in just a second. So if I have the kinetic energy is 1/2 mv squared, or following this, p squared over 2m, this gives me my total energy for the oscillation, p squared over 2m plus 1/2 kx squared. Okay, that's the classical result. And so what you get when you have the classical result is this energy can be any possible energy, and it turns out that it looks something like this. If I were to plot energy as a function of this displacement r, and so here you have the equilibrium value, and at high r, you have the energy comes up, and it's mostly potential energy until it stops. And so then there's zero kinetic energy, and then it becomes purely potential, and then the restoring force causes it to go back the other way here to where there's no potential energy and it's all kinetic energy, and then it comes back again. And so the potential energy is stored within that spring, and so it's motion as it goes back. And if you know, and I encourage you to do this, stick your hands out and start to like oscillate back and forth. So if your shoulder distance is equilibrium, this is going to be stretching it and then compressing it. And so there's a point to where you stop moving and then it comes back. And then there's like that moment where you've got zero kinetic energy, full potential, no potential, all kinetic, zero potential, all kinetic, back and forth again. Okay, helps to play with the spring. All right, but notice that any possible energy is available because there's no restriction on what kx squared can be or the momentum can be. Classical result. It's about to change because quantum is going to quantify the crap out of this. Okay. Okay, so classical result, the total energy is equal to p squared over 2m plus 1/2 kx squared. The quantum mechanical result requires that we have a wave function that dictates the motion or dictates or describes the entire system. And we have a Hamiltonian operator. Our total energy operator is equal to minus h bar squared over 2m d squared dx squared plus, now we've got the potential energy, which is going to be 1/2 kx squared. Okay, so note the difference between the classical p squared over 2m and the quantum mechanical minus h bar squared over 2m d squared dx squared. So this is the difference, the main difference between the quantum mechanical approach of the total energy operator and the classical approach. But notice there's a squared over 2m and a squared over 2m. So there's a link between the two, but there's slight differences because this is eigenvalue, this is continuous. Okay, so what we're going to do is we're going to solve the Schrodinger equation. And by solving it, I mean find the wave function such that this whole equation is true. Okay, and we're going to get energy values corresponding to allowed energy states. Okay, and from the podcast that you listen to, hopefully you've already looked in the picture in Atkins and you can see those quantized energy states. That's what we're going to find. But in order to do that, we have to find a wave function that fits this kinetic energy, but also with this potential. This is something that was different than the particle in a box. Before, we didn't have a potential. We just had a box. Okay, so we had our, oops, this is our wave function, and we had some 0 to L, and it was great, and we had just a box or a point in the middle, and we were figuring out what the wave function was. This time, however, let's put the energy here, we have, actually, no, I should do this way, all the way down. There we go. Now we have a boundary within the box that follows this potential. So this potential causes this part. So now what we need is a set of wave functions that are going to look something like this. Actually, those are the squared, but okay, I'll leave it as that. Okay, so we have now, not only do we have this changing potential, but now we're going to have extra constrictions on how those what wave functions will fit within this system. Okay, so the goal here is to, actually I want to pause and erase this bit. Okay, so the goal is to solve h psi equals e psi, which is minus h bar squared over 2m d squared dx squared plus 1/2 kx squared. All of that operating on psi equals psi, or equals e psi. All right, so what we're going to get, I'm just going to jump to the answer. We're going to get quantized energy states, these blue lines that I'm drawing across. Okay, so we're going to get quantized energy states that are going to look like E subscript V, that'll become important in a moment, 1/2 plus, oops, yeah, sorry, V plus 1/2 H bar omega. All right, now this V here represents the vibrational quantum number. So that's the quantized number that's changing, like the N was associated with energy states. So V is associated with vibrational states. H bar you're familiar with. Omega is the frequency. And it's related to square root of Kf over m, where this is the force constant. And this is the reduced mass. Okay. Go team. So we're going to show that this is true. But the way we're going to show this is true is by guessing a wave function. We're not going to guess a wave function. I'm just going to tell you what it is. But I want to talk about the restrictions that have to happen for this particular wave function, because this wave function is unique because it has to fit all these conditions. Okay, so what conditions does it have to fit? Psi must have the following. Number one, it needs to go to 0. So psi needs to go to 0 more slowly at the farther displacement. Needs to go to 0 more slowly at farther displacement. What does that mean? Well, let's come back over here and I'm going to erase some of this. So let me draw this again so I can draw it in as we're talking. Okay, so here. Okay, so our equilibrium. Okay, here is the equilibrium position. Small displacement, big displacement. Small displacement, big displacement. Okay, so the farther away you are from this equilibrium, the bigger the displacement. This says that the wave function needs to go to 0 more slowly at farther displacement. Well, I know that my wave function has to equal 0 at this boundary, and it needs to get pretty damn close to 0 at this boundary. So close to equilibrium, my wave function needs to go to 0 quickly, whereas far away from equilibrium, it needs to go to equilibrium much more slowly. Okay, and so I need, and actually this is not really making much sense of it. So none of this, so this one doesn't go to 0 until it reaches the very edge. It just keeps on going in the middle. Whereas this one will reach 0 pretty darn quickly. Okay, and so the farther away from displacement, it has to reach 0 more slowly. All right. Number 2, larger mass, faster decay. Okay, so this comes from the energy is directly proportional to this frequency here, but the frequency is inversely proportional to mass. So that means that, as well as semi-directly proportional. So it's under the square root. But if this is a bigger value, this needs to be smaller. Okay, so that means that it's going to have a smaller energy associated because it's going to have a smaller frequency. So this becomes, because larger mass, faster decay, which means a smaller frequency because of that inverse relationship. Okay, now you might think, well, but that doesn't make much sense because how is the decay rate part of the energy? Well, the energy is dictated by which wave function fits. So if this wave function changes, the energy is going to be different that satisfies the Schrodinger equation. So if we have a different wave function, we have a different energy. And so we need to make sure our wave function is such that we get an energy that's going to be accommodating to the fact that faster oscillations happen with smaller masses. Okay, number 3. The box is wider at the top, which means larger energy states need broader wave functions. So larger energy states need broader psi. And I've kind of already shown that, that as you get up higher, you're going to have more bumps in your wave function, and they need to be broader as you get closer to this potential boundary. And so up high, you're going to have a much broader wave function, and then down low, you're going to have a much shorter one. Okay, and actually, I'll draw a couple more in between. Well, there we go. Okay, cool. All right. So these are the constrictions that we, or the restrictions that we have on the wave function. And so it would be great if we could combine all of these things into a single formula for a wave function, and then it would work. So in the next video, I'm going to show you what that wave function is and how to use it. Go team. That's a lie. I'm going to continue and just give it to you now so it's in both videos, because that way I at least know that you've seen it. Okay, so these are the top 3 things that we need. So now I'm going to jump ahead and write down what it is. So the wave function for the harmonic oscillator in one dimension is equal to n sub v, h sub v is a function of y, e to the minus y squared over 2. Yay! Where y equals x over alpha, and alpha equals h bar squared over m k f all to the 1/4. Go team! So this is the wave function for quantized vibrations. Here you have a polynomial. This is a polynomial function that we'll get to in the next video. And then here we have our Gaussian. So the Gaussian ensures that it goes to 0 more slowly, and then it becomes broader because of the polynomial. Cool. And then there's some simplifications here that just make this prettier. All right. So in the next video, I'm going to dive into what all of these things mean and prove to you that it does, in fact, satisfy the Schrodinger equation. Go team.